Hello, in this video I want to discuss a LinkedIn post that I made about one of the winners of Fields Medal this year. Professor Yu Dang won Fields Medal for his contribution to the Hilbert 6 problem. So there's a really nice video put out by the Simmons Foundation about his work and also some nice animations and stuff you can hear about his life. I also heard about this actually about a year ago from a YouTube video about Science News. Is this video right here, and they talk about the ideas involved in the paper as like a very high level, which I think is a great video to watch. One thing I wanted to comment about is because I have a little expertise in the field of mathematics, so I have a PhD in functional analysis, and I have some exposure to kind of the statistical mechanics ideas. I took a statistical mechanics class, or I sat in on it. And so what I did is I went and watched the seminar presentation here, and then also 3 presentations by Professor Dang about his research, and I just wanted to make some comments from what I got out of it. So first thing is that one of the things that you learn in statistical mechanics about a gas, like so for instance you're in a class, you learn about like the billiard ball model of a gas. So you imagine that a gas in a container made out of a bunch of balls, and they're bouncing around and they're hitting the edges of the container, and that's why the gas exerts pressure, and the temperature is related to how fast the particles are moving and stuff like that. So you learn about this model for how a gas works. However, there are also equations that relate the gas on the big scale. So for instance, you have like the standard gas law, you have a bunch of different laws and equations that are related to how the gas behaves from your perspective. And then there are also certain equations like Newton's laws that tell you how the gases behave on the very small level, like individual particles. So one thing I want to mention here also is that what he does that's a little different, and how he was able to make this big contribution, is that he had a certain combinatorial representation. What that means is he has this different kind of a way of counting and classifying different things in an organized kind of way. He has to kind of organize things so that he can manage a bunch of stuff. And in my thesis, my dissertation, one of the things that I did is that I had to do something kind of like that, but it, obviously not as complicated. But it's something that happens in math a lot of times. You have a certain problem, and then you want to break it down into different parts. And then maybe one part is the really good part, and that's the part that you really like. And then there are different parts that you don't like. And you don't like them because they behave weirdly, or they don't seem to be behaving in a certain kind of way that you think that the whole thing behaves like. So you break it up into a bunch of different parts, and you actually, and this is like one method, is that you take the parts that are badly behaved and you actually show they're not actually that important. They actually don't contribute very much. They do come up, maybe they're spread out their influence, but the thing is that overall, the thing that is most important, the thing that gives you the thing that you want to see, is actually the most important thing. It's the dominant. So anyway, what he does in his paper is that, well, in their paper, because it's he's working with a bunch of co-authors, they use a certain combinatorial algorithm to break up a complicated structure, and I thought it was really interesting. Also, last year, when I learned about this, I emailed Professor Dang, and I wanted to hear his thoughts about his research and how it was being accepted by the mathematical community at the time. Well, obviously, since then, obviously he won the Fields Medal, so this is like the stamp of approval that what he's done is one of the most important things going on right now. And this is a quote that I have from him. So Hilbert's original program calls for the derivation of fluid equations from particle dynamics. So that's like the big scale, like, equations like Navier-Stokes equation or Euler equations, those kinds of equations that you can use in like an engineering class about how fluids behave. And particle dynamics, that is like Newton's laws for individual particles via Boltzmann's kinetic theory. So that's like the stepping point between fluid equations and particle dynamics. It is known since grad 1949 that this route is expected to be valid only in the Boltzmann grad limit. This is when n epsilon to the d minus 1 is equal to 1. So basically how these limits work typically is that you imagine a box, and in the box there's a certain number of particles, usually n, and then epsilon, I guess, is the size of the box or something. I don't really remember exactly. But when you do these certain kinds of limits, the hydrodynamic limit or something like that, what you imagine is that there's a bunch of particles in the box, and the box is going to, it starts off very small, and then it starts to grow. Because you actually don't want to talk about just a very small box, because when you're doing this kind of physics application, you want something that's like macroscopic, which is like the size of something that's like relative to the size of human beings. You don't want something that's like the size of an atom. So what you imagine is a box that's pretty big, but because it's very big, there are a lot of particles in it, because the particles are very small. Now the question is, well, how do you like scale it up? Do you just make the box really big and you leave the number of particles in there small? Or when you make the box bigger, you increase the number of particles? Well, that's what this kind of limit represents a lot of times, is that when you make the box bigger, and so it goes from being very, very tiny to being something that's visible, while it's growing, you want the number of particles to be increasing. But you want them to be increasing at a certain rate that's relative to the amount of things in there. So this is some kind of representation of how the number of particles are growing while the box size is growing. So as he said, it's valid, expected to be valid only in this certain limit. Our contribution in Hilbert's sixth problem is in this direction. Of course, there is still the open question to derive fluid equations from particle dynamics without going through Boltzmann. This scenario includes more general scaling laws, such as the case n epsilon to the d equals 1. This is the dense gas case. This question is physically very important and mathematically much harder. In our paper, we take the road more traveled that corresponds to Hilbert's original program, hence the Boltzmann grad limit. Of course, there are still very many important open questions to be investigated in the future. So what he's saying here is that you have a certain kind of a limit case where the number of particles and the size of the box are growing at a certain rate. And then this right here is a different rate. And this, I believe, is where you have basically more particles. So there's more collisions between the particles. And so it's harder to keep track of everything. So in my, also on my LinkedIn post, I have 2 papers that he had. These are LinkedIn papers. Archive papers. This is the video that's up there. And these are the presentation videos. So now I wanted to go over to the papers and make some comments. So we have here, this is the abstract, and in this part right here is that he kind of explains the main idea, which is the general strategy follows the paradigm introduced in the first 2 authors. This based on propagating a long-term cumulative ansatz. So we'll get to the word ansatz later, but basically it means a paradigm. So we take our particular thing that we're trying to handle and we give it a framework, we give it a way to interpret it. We break it down in a certain structure, and then we use that structure to get us what we want. And this ansatz keeps memory of the full collision history of the relevant particles, and then he shows that the smallness of these cumulants in a certain kind of estimate. Okay, so I wanted to make some comments about the paper. So this is the idea, is that individual particles, they behave like Newton's laws, which you have individual particles, when they come together and they hit each other within a certain distance, they then bounce off. Okay, so, and I believe here epsilon is, so this is the center of the 2 colliding particles, which is epsilon. So basically this is like the size of the particles. So what I would imagine is, if you go back to his statement that he gave me, is that the n epsilon to the d is related to the number of particles and the size of the particles. This right here represents the way that the particles behave. And this right here represents the part that's really nice, which is going to satisfy what he wants to satisfy Boltzmann's equation. And then this right here represents the different kinds of ways that particles can get connected to each other. So Basically, if you start off with the probability distribution and you imagine that all the particles are independent, then like you imagine a big pool table and you have a bunch of balls on it and you hit the balls. Well, they start to move in a certain kind of way, and as long as they don't hit each other, then the way that they're moving just depends on how you initially started hitting them. If I look at one ball, it only depends on how I hit that one ball. But once it hits another ball, then the information of how that ball is moving depends on not just itself, not on the way it was moving earlier, but also on the way that the other particles that it ran into along the way were moving. So this right here captures a lot of those kinds of interactions between the two. So one thing that he does in this structure is he does this thing called time layering. So what he does is he breaks up the whole time period from 0 to t. So this is like a time from 0 to like the end time, so t fin. So it may be like from 1 to a minute or something, right? And then what he does is he breaks it up into smaller intervals. So instead of from 1 to a minute, he then has 0 seconds to 1 millisecond, and then 1 millisecond to 2 milliseconds, and 2 milliseconds to 3 milliseconds. So what he did is he broke this whole interval up into a bunch of smaller intervals. And although these intervals are small, they're not like length 0. They actually have a length. It's just sufficiently small. And what that means is that I just chose the time length to be really small, like millisecond or something, just so it's small enough that when I do my certain kinds of estimates and I calculate certain things, I could put them together in a nice way. This is like when you do an integral in calculus, where you break the area up into a bunch of Riemann sums, which is a bunch of rectangle areas. Now what you can do is if you just make the rectangle small enough, then the area of a rectangle is basically the area of your curve. And this is kind of the same kind of idea, is that you break something up and that has a finite length into a bunch of smaller, much smaller finite lengths, but a lot of them. But now that because they're smaller, you actually can manage them in a better way. Just like when you're doing calculus, if you want to calculate the area under a curve, like if you have like the area, you want to calculate the area under this curve right here, it would be much easier if the curve was basically made out of a bunch of rectangles. Now, if you zoom in on the curve, you take this little part right here and you zoom in on it, it basically looks like a horizontal line. So this little curvy part right here basically looks like a horizontal line. So the area underneath that curvy part is basically a rectangle. And that's kind of like the Calc 1 kind of thinking. And this is one of those things that happens a lot in analysis. You pick something that's big, you break it up into a bunch of small parts, and then you manage them independently. So one thing he does with this time layering, he breaks it up into a bunch of small intervals. And then what he needs to do is he needs to control how the system is behaving. So he doesn't actually control it, but what he does is he's controlling his understanding. So mathematicians use this word like control. He broke it up into two pieces like over here. This part right here is going to start to behave. It's going to start to behave like the Boltzmann's equation. That's what he wants to show. And then this is the really bad part, the part with all the weird interactions. And he wants to show that this thing doesn't actually contribute that much. So this right here is the ansatz. So what he does, he has it broken up in a particular kind of way, and then he's going to use this as a stepping stone between the different steps, but between the time layers. So what he wants to show is that there's some kind of estimate. So this right here is that kind of cumulative expression, and then he's calculating an L1 norm of it. So that's just a particular way of measuring how big something is. It's a function, how much area is under the curve. That's basically what L1 is. And he wants to calculate this, and he wants to show that it doesn't have that much area. It doesn't contribute that much as far as probability is concerned. However, and when he does this, he actually talks about another paper, what they do is they show that if you assume that in earlier time, so this is the earlier time, that you have an L infinity bound, what that means is you have a different kind of estimate. You have a certain type of understanding of how big something is, a different one. If you have this different understanding, the L infinity one, then you can get the L1 kind of estimate at time L tau. So from the earlier time, you can get to a later time, but you have to assume a different type of estimate to get the new estimate. So if you imagine breaking it up from 0 down to tau, down to 2 times tau to 3 times tau, and then dot, 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 all the way down to t. From each step, you need to be able to carry enough information to justify going to the next step. So this is one of those things that happens in induction. So if you have an induction hypothesis, so if P of n, then P of n plus 1, and then P of 0 or something, P of 1. So the way induction works is that you assume the base case, there's an initial starting case, and then you assume that when you go from one step to the next, it always works. You can always go from one step to the next. However, if you start at 0 with this L infinity estimate, then you can get to tau with the L1 estimate. But then once you're at tau with the L1 estimate, you can't get to 2 times tau with the L1 estimate. You can only go from L infinity to L1. But then once you get to L1, you can't use L1 to get to L1. So what happens is you get stuck. You can't continue the process. And that is what he talks about here. He says that it's not possible to obtain smallness of at L tau from knowing smallness at the time right before it if you're using the same norm. So the same way of estimating how big the cumulates are. And he explains why you can't do this. So what he does is instead of just trying to just estimate it, what he's going to do is something different. What he's going to do is he's going to go back to this original thing. And then instead of just throwing this thing away and saying how big this thing is, and then just trying to estimate it, what he's going to do is carry some of that information along. So instead of going from L infinity to L1, what he's going to do is he's going to go from 0 to tau to 2 tau to 3 tau, etc. But he's going to carry some of the information that this thing captured. He's not just going to throw it away by saying, oh, it's really small in the beginning. Because what happens is if it starts very small in the beginning, then he can't just keep saying that it's really small because it starts to grow. What he needs to do is carry some kind of information along the way so he can justify all the way at the end saying that it's not very important. So what he does, he wants to propagate. So that's the thing. He wants to carry through in every step. Structural information. And so what he does is he represents the cumulants, these things that are in this product, all this stuff here. He represents it using these diagrams. And let's see where the diagrams are. They're in his videos. Diagrams like this. And so he has a certain kind of algorithm where he breaks them up into certain ways, because what happens is they get kind of complicated. And I did watch the videos. It was about a year ago. But there's a lot of interesting stuff here where he talks about the kind of algorithm. And the reason he has to cut them is so that they're organized in a particular kind of way, because the way the particles can hit each other, there are certain things he needs to calculate and estimate, and it's very complicated. As you can tell, this is like a 200-page article, 200-page paper, which is, there's a lot going on here. But that's why he won the Fields Medal. In this other paper, he also has the part where he goes from Newton's laws to Boltzmann's kinetic equation to these hydrodynamic equations. So like Navier-Stokes equation or Euler equations. And so based on some of the ideas that he was using in the other paper. Okay, so I just wanted to make a video talking about some of these ideas that I mentioned in this post, and also point you to some of these interesting videos you can watch. This one right here I thought was pretty good. And this one right here was also interesting. I hope you have a nice day.